There we go. So, sorry about that, and thanks for reminding me. So we're reviewing exhaustive alkylation, and we're here doing an example of exhaustive acylation. It's very simple, just wherever you see an OH, replace that alcohol functional group with an ester functional group, and just be sure that you use whatever is the acyl group that you're given. In this case, our acyl group is this one. So you just tack that on in place of the hydrogens on all of the alcohol's sugar functional groups. I have to plan to fit it in. So bond angles and such are going to go out of the roof. Chair form is not glucose. No, that's, oh, this one, yes, that is not glucose. And I don't know what it is, but it's this oxygen here that's axial that makes me know that it's not glucose. It's easier for me to tell with the chair form, well, also the straight chain form that we've just memorized is right, left, right, right. So I don't know why that is, that all of the OH groups are just happen to be equatorial for glucose of all things. I don't know why that is. I think it's just a coincidence, but you know, I'll take it. So this is an example of an exhaustive acylation. And I mention that because, oh wait, CH2O acyl group, C double bond O, phenyl. And of course, you guys recall pH is a phenyl group. It's basically a benzene ring. And if you don't like pH, or you can also write C6H5. Perfectly acceptable. Everyone will know what you mean. There's really only one common, one way to put together 6 carbons and 5 hydrogens that's common at all. So you can substitute C6H5 for pH if you prefer. In any case, yeah, I think now we've got all of our acyl groups in. I just am missing a hydrogen. There we go. So the reason I wanted to mention all these is we're still not quite done with reacting at sugar molecules' oxygen atoms. I really would not mind also reviewing these redox reactions we did, because I think we're going to have plenty of time today. But maybe what I'll do is, just to make sure I get through everything I was going to discuss, any time left at the end of class, I won't start the next chapter today. I'll go back and also review these redox reactions that we did, just to make sure that, to be completely honest, partly for my sake, so that I remember them also, because they're not something that I deal with constantly. In any case, we've learned how to replace every single last one of these OH groups on a typical cyclic form of a typical D-aldohexose with alkoxy groups. In other words, how to convert all of the OHs to ether functional groups. But there's another type of reaction that we can do that in many ways is more relevant to what goes on in biological systems, particularly when we start to consider disaccharides and polysaccharides, which are kind of important. You know, certain important polysaccharides include things like, starch, glycogen, cellulose. Like, these things are not unimportant species. They play large roles in living systems. And so the good news is, once we understand the structure of simple monosaccharides, and once we understand also the formation of glycosides in general, disaccharides and polysaccharides are very easy to understand. They're kind of a pain to draw, and I don't know how much I care as to whether you guys can draw any given disaccharides, trisaccharides, polysaccharides, but it's okay, because you can understand the structure. that's not a word, sorry. Glycosides, IDES. Glycoside formation, let's say. And in making what's known as a glycoside, we're not going to react all of the OHs on the sugar molecule. We're only going to go after the one on carbon 1, the one that's after the one that's at the so-called glycosidic carbon. So let's make another 6-carbon sugar. Let's stipulate that we have only the downish or alpha anomer. It's not going to matter in the end, as you'll see. Let's see, which one do you want this time? Maybe I'll put my OH up here this time. So again, not glucose. I don't know what it is, and I don't expect you to either, but it's not glucose. What kind of professor would expect something of his students that he himself or she herself doesn't know? I don't want to ask that because you're probably going to start giving me names. Don't tell me I don't want to know. That question was rhetorical. Now I should say, you'll notice this CH2OH group is also equatorial. I believe if we were to switch that one to axial, that we would then be looking at an L sugar. I'm 98% certain that that would be the case. Good, but so we've learned how to react all of those OHs. There's also a way to react just the OH at carbon 1, which is called the glycosidic carbon. And carbon 1 also is the one that used to be an aldehyde functional group in the straight chain form. So of course, we talked about how you get this hemiacetal. This grouping of atoms here fulfills the definition we gave in chapter 9 of hemiacetals. And so formation of that hemiacetal is very favorable. This is, again, we would call that the pyranose form. You also have your furanose forms. I don't ever really work with those, and I certainly don't care if people memorize those, but there's also a way to get 5-membered rings. In that case, rather than the oxygen and carbon, let me get this right now, on carbon 5, forming the hemiacetal, see how this oxygen is attached to carbon 5. Instead, I believe you'd use this one that's attached to carbon 4. And if you make a hemiacetal there, then you'll get a 5-membered ring rather than a 6-membered ring. And of course, there's 2 different isomers. We call them anomers. You can have the OH pointing down, which is the alpha anomer, or the OH pointing up here, which is the beta anomer. And those can be interconverted. Both of those hemiacetals can be made starting with the aldehyde functional group. So then, just to reiterate, we've seen that you can react all of those OH groups, but there's a way to react only the OH group at carbon 1 and none of the others. And the reagents are pretty simple. You'll just take an alcohol. This could be ethanol. I'm okay using ET for ethyl group, right? CH2CH3. And you also need an acid catalyst to get this done. And this turns out to react only at carbon 1. What is the substrate? I'm not sure what you mean. The molecule that we're acting on is this one. That's the one that we're going, whatever it is. Oh, you mean what's the name of this? I don't know, but it's not glucose. It's different at carbon 2 and 4, isn't it? So whichever that one is. Yeah, I don't know, and I wouldn't expect you to, except, again, except as far as to say whatever it is, it's not glucose. So anyway, if you heated whatever this D-aldohexose is in its pyranose form with in acidic ethanol, what I would expect that you would get would have reacted only at the anomeric OH. And so you will get an ethoxy group here. And again, this does not have to be methanol. This does not have to be ethanol. It can be any simple alcohol. You could use methanol, isopropanol. The only one that I bet you could not use here is our old friend phenol. Remember, phenol is special because it's so much more acidic. than alcohols like ethanol. That makes its reactivity somewhat different. So all of the other OHs will be untouched. And we'll get to why that is in a second, since there's, I think, a fairly easy to understand reason as to why that is. Again, this is not the same type of reaction as when we were doing exhaustive alkylations. This will give us an alkoxy group only on carbon 1, only on what used to be the aldehyde carbon. What is the reason, again, about not using phenol? I think phenol's too acidic. Phenol doesn't generally react exactly like aliphatic alcohols like ethanol and methanol would be. And I think I think we'll learn some other examples of phenol's reactivity being different when we get to chapter 10, I guess it is, on carboxylic acids and esters. So, but as you can see, all of the other OHs are untouched. At least I hope they are. I'm just making sure I didn't move any of them. Nope, we're in good shape. So it's only this one that's going to react. And actually, as a matter of fact, to be completely strict about it, you will also get the other anomer. So even though we started with the alpha anomer, once you make the so-called glycoside, here I'm using the word over here, and the definition of a glycoside, I'm giving the definition using a structure. Glycosides are compounds like you see here. But you will get both. This one happens to be the alpha anomer, and this one happens to be the beta anomer. So, but in both cases, all of the other OH groups will be untouched. And there's a very good reason that, that the other OHs are untouched. It's because the other OHs are all ordinary standard alcohol groups like you'd find anywhere, but the OH in the anomeric carbon isn't. That's a hemiacetal OH. And what that means is that effectively carbon 1 is actually an aldehyde carbon because this cyclic form, recall, is in equilibrium with the straight chain form. And so that means that carbon 1 has a special reactivity. It's not like any other run-of-the-mill alcohol functional group. But instead, you can do reactions there that you wouldn't normally expect to happen. And indeed, we wouldn't normally expect run-of-the-mill alcohol functional groups to react with acidic ethanol. We've never seen a reaction of that type where you'd get any kind of rapid or clean reaction. But we do know that aldehydes and ketones can react with an alcohol in an acidic medium. And that's effectively what's going on here. So the fate of the anomeric OH, by the way, that's going to wind up in a molecule of water. So, but these ethoxy groups all come from ethanol. So these oxygens come from the ethanol in this case too. It's not just sticking an ethyl group on here. It's actually the entire ethanol molecule is reacting with the sugar molecule. And so you go from making a hemiacetal to making a full acetal. So this is now a full acetal functional group. That's another way to define glycoside, if you like. You're converting the hemiacetal to a full acetal. And you will get both, by the way. Even if somehow we started with the pure alpha anomer over here, you will get both alpha and beta in the end. Can't be helped. So you will, in fact, get both. That's kind of a minor point, but I figured I kind of wanted to tell you because I feel like my role here is at least in part to tell you the truth. And so that is the truth, that you will get both. But the reaction is the reaction and also the mechanism, though we didn't go over the mechanism and I don't expect you to be responsible for it. But the reaction and the mechanism we went over in chapter 9. We just went from a hemiacetal to a full acetal. And so this is not a new reaction for us. But that also explains why it leaves all of the other OH groups untouched. You can't form acetals there because those aren't aldehydes or ketones. But carbon 1 is actually an aldehyde carbon. This can open back up to the straight chain form, which is an aldehyde group. And on that, you can make a full acetal. So that's why only that one reacts. But again, this does not have to be only ethanol. It can be any other simple alcohol. As we said, except I would expect it wouldn't work with phenol. I'm not aware of a good method for making phenyl acetals. I doubt, I mean, I don't have experience doing that reaction or ones like it, but I just would be very surprised. I mean, I've made other acetals and hemiacetals, and I guess based on that experience, I would be very surprised if that would work with phenol. I bet it wouldn't, but pretty much the sky's the limit otherwise with the alkyl group we've got here. Good, so these two, these aren't enantiomers, by the way. These are diastereomers, right? Because only the configuration of this carbon changes. All of the other ones change. So, but you would get a mixture of these two, yes. That's what I would expect. Even if you started with a pure diastereomer here, I'd expect you'd get a mixture here. And I don't know that it would be 50-50, but it would be a mixture. Yeah, and I think that's all I really need to, yeah, and that's in your class notes too. So I just wanted to make sure that I'm taking care of everything that's in the class notes. So good, so that just leaves one other thing to cover, and we're at not quite 3:25, we have until 45, so I bet all of the chance to review these redox reactions, but I wanna take the time to cover how it is that multiple sugar molecules come together to make first a disaccharide, then a trisaccharide, and so on and so on. How it is that eventually polysaccharides get put together. And these things are getting really big, and I don't know if I care very much that you can draw these things. As you know, the exams are going to be multiple choice anyway, so I wouldn't be grading your structure drawing directly anyway. But whether or not you can actually draw one of these, I think these structures, as big as they are understandable once you break them down into their pieces. And that's what we're going to do here. So if we understand how to form a glycoside, well, we're going to take carbon 1 and react it with an alcohol in order to go from a hemiacetal to a full acetal. So what if we did the following instead? What if instead of a simple alcohol like ethanol or methanol or isopropanol or benzyl alcohol, what if instead we took some OH group from another sugar molecule? And you're all thinking, Dr. Wass, you're so evil. Well, not really. I mean, other than that, there's no difference. We'll get a full acetal, but instead of an ethyl group, this OH is going to get attached to another sugar molecule. And yeah, you get something very big, but I don't think it's beyond what we can understand. So let's consider forming a disaccharide. So let's start out drawing another glucose. And here at the anomeric carbon, we're going to make a full acetal, but instead of using ethanol or methanol or benzyl alcohol or isopropanol or whatever you like, we'll use one of the OH groups on another glucose molecule. Which OH? Well, it doesn't really matter. In principle, you could take any of them, and you would get a different disaccharide each time. But let's also make this in the beta position, though you could certainly form, you could certainly make the alpha one as well, but let's draw all these things in. The rest of the sugar molecule is going to be unaffected, right? Since we said that at the other OH groups, those don't react. But we're about to do the very same thing we just talked about. Except instead of treating it with a simple alcohol like methanol or ethanol, we're instead going to use an OH, oops, that's just hydrogen. We're instead going to use an OH group on another glucose molecule, and it doesn't even need to be glucose. And by the way, if we connected a glucose and a galactose in this way, galactose is just like glucose except it differs at C4. And if we used the right oxygen, I think it actually might be on the oxygen in carbon 4, but whichever, I just don't know off the top of my head, whichever one that is. And if you connect a glucose and a galactose in that way, you've got lactose. And so that's, again, the milk sugar that we were talking about the other day, that people are sometimes of lactose intolerance. Good, so just to make things somewhat easier to see, I think I'll choose to attach, which should it be, this one or this one? Eeny, meeny, miny, mo. Let's do this one. So I'm going to use that OH in place of the OH group in ethanol that we did in the previous page. And so that means that this oxygen is going to be attached to the ring here. And so we'll just drop that in there. Meanwhile, the H that was on, wait a minute, hold on. Meanwhile, the OH group that was here and the H that was on this oxygen, well, those will come together and make a molecule of water. So that's where this oxygen is. This oxygen there, I just want to be sure that everyone's following me. That's the same oxygen as was in this other sugar molecule. So now we'll just copy the rest of it out. And we will get, as a result, a disaccharide. And I didn't have to pick this OH. I could have picked this one. I could have picked this one. I could even have picked that one. Now we should be in good shape. So if you compare this to what we did on the previous screen, it's the exact same thing. If you understood what we did with ethanol that time, we did the same thing, except instead of an ethoxy group, we have a whole sugar group. So any two OH groups can connect. Well, you need one of them to be at carbon 1 of one sugar, right? Because that's the only place you're going to be able to get a full acetal. Notice how once again we have an acetal functional group over here. But in terms of the other one, yeah, the sky's the limit. Any one of those OH groups can react. They will do the same type of reaction that the OH group in ethanol did. And the reason I mention this is I think in your upper level classes, you're probably going to encounter disaccharides, trisaccharides, polysaccharides, oligosaccharides. But I think just with this, I mean, we could go on, but I think I don't really feel like attaching another. And if I don't, I can only imagine how much you guys don't feel like it. But I think you get the idea that if we wanted to, we could do it again with carbon 1 on this sugar and maybe stick some different OH on there and make another full acetal. And again, and again, and again, and again, and again. You get the idea. If you can imagine doing this once, you can imagine doing it an arbitrarily large number of times. And so that's basically how polysaccharides are put together. That's how you get your starch and your cellulose and your glycogen and all these other things. They're just made by putting together individual sugar molecules. I think all of the above were all glucose molecules. And the only thing that differs is in part whether this oxygen is alpha or beta. That's one thing that affects it. And the other is which of the other OH groups on the next glucose is involved. So varying those two things will get you different polysaccharides with different properties and different names. But the idea behind it is the same. And so, and again, I don't know what they are off the top, and I sure don't expect you guys to memorize it. But one of those possibilities, if you keep doing it, will give you starch. Another one will give you cellulose. Another one will give you the other thing that I've been talking about that just went out of my head, glycogen. So they're all similar conceptually. And as I said, if you can imagine changing this to O-ethyl or O-isopropyl by using ethanol or isopropanol, then you know everything you need to know to understand what's going on here. It's just instead of a simple alcohol, we're using an OH on a much more complicated one. Did you say alcohol at position 1 can be alpha or beta? Absolutely. And we would expect in any given one of those polysaccharides, they'd be always the same. This one is pointing up, so I guess that one's beta. And so you would expect if this pattern continued, they would be all beta, because these are biosynthesized using enzymes that are very particular about such things. But other disaccharides and polysaccharides use the oxygen in the alpha anomer. So either could be used in principle. But I guess my point here is simply that if you understand forming a simple glycoside using ethanol or methanol or some other small alcohol like that, then forming a disaccharide is exactly the same thing. There's nothing else you need to know in order to understand it. except instead of taking a small simple alcohol and using the OH on that, you're just using one of any of the many OH groups on another sugar molecule. That's it. There's otherwise no difference conceptually between the two. And it's like I said, and I think I even put in the class notes that you're not going to be responsible for any of these biological function sections of the chapter. I don't think that belongs in an organic chemistry class. Nor, as I said, do I expect you guys to memorize particular disaccharides and polysaccharides. I think you should take a look at some of them. I think it will interest you to see the structure of sucrose, which is table sugar. It's a disaccharide involving glucose and fructose. Some of you may be diabetic or know someone who's diabetic, so you know sucrose is an important molecule. It might interest you to see the structure of lactose, especially if you or someone you know is lactose intolerant. So certainly do take a look at them. Don't avert your eyes when you see these structures in the chapter. They won't hurt you, but I certainly don't expect you to memorize any of them. I don't think that's the goal. As I said, if you know glyceraldehyde, if you know D and L glyceraldehyde, that's all you need to know to understand other D and L sugars. And I think if you know glucose in the straight chain form, I'm pretty happy. I don't see any need to go further than that. Good. So much then for disaccharides and by extension polysaccharides. That leaves me with a good 8 minutes to review these redox reactions of simple sugars. Any other questions on these structures? I hope I've convinced you that as large as a structure like this is, we can manage it. Ladder what? Yeah, but as big as this thing, as big and ungainly as this thing is, we can analyze this and understand what's going on here. But no, I certainly would never, which of the following is mannose? No. Nope. Good. Well, so like I said, you can pause the video on YouTube if you would like. Let me go back to some of our straight chain forms. Actually, well, first of all, I don't know why I'm doing it so small. This is something I just learned just now teaching your class. If you draw those first and then the straight line, the vertical straight line, it's much easier. Mine's a little bent, but oh well. Let's do left, left, right, right for no particular reason. And no, I have no idea what that sugar is, but I know with the OH I'm putting in now, that makes it a D sugar, and I know that it's not glucose. And that's certainly all I would expect you to know. Good, so you'll recall that we said that you can treat a simple sugar like this, and I'm putting it in the straight chain form just because it's easiest to see that way, that you can treat this with sodium borohydride, which is a reagent we learned in chapter 9. And usually the solvent here is an aqueous alcohol mixture, aqueous ethanol or aqueous methanol. Either way is fine. That's just the solvent. That's not going to react to form our product. But in so doing, I would expect that we would get the so-called sugar alcohol, or alditol as it's also called. Oh, didn't use my rules here. But all of the other OHs will be unaffected. Unsurprisingly, there's nothing else in the molecule that can be reduced. So all of the other alcohol functional groups are just along for the ride. So this is your sugar alcohol or alditol. You need H2O in part because what you're actually going to wind up with at first is CH2O minus. And again, we're not learning the mechanism, but we need something to put that proton back on and give us a neutral product. And it's also partly for dissolving. Both water and methanol are just to dissolve everything. We need something pretty polar because the sugars like this in general tend to be quite water soluble. So we need something that just will dissolve everything for us. And also just a reminder, the same thing will be true if we used lithium aluminum hydride. Only thing is then we need to use 2 steps. The first step will have the LAH in an aprotic solvent, diethyl ether, phenol. No, usually it's a methanol or ethanol here. Phenol's a solid at room temperature anyway. You want something that's going to be a liquid and dissolve everything, and also be reasonably easy to get rid of later on. Now here I'm not using ethanol, I'm using diethyl ether. So I always warn my 227 students about that too. We need to use an aprotic solvent here. Reason being that lithium aluminum hydride is much, much more reactive than sodium borohydride. And sodium borohydride does react with both water and methanol, in fact, but it reacts with them very much more slowly than it reacts with the aldehyde groups. So it's well controlled, it's not a problem. But we can't have anything protic around if there's lithium aluminum hydride. And I talk in the class notes about why you have this difference in reactivity. So you can't have anything protic or you'll have a big fire on your hands. And trust me, if you've had unintentional fires like I've had, trust me, it is not fun. And only then in the second step, then we add the water, only after the reaction is done. And very, very carefully, so as not to give us a big fire. Actually, I've done a lot of LAH reactions in my life, and the way I love to do it, my preferred way to work the reaction up, is I'll take the top off the flask and pitch in little by little pieces of ice. And so it's still an exceedingly violent reaction. You got to go very slowly and carefully. But no, the opposite, I'm not a pyro. I do not like fires. Good, so, but that will give you the same result. You'll also get the alditol. And we made, that's nothing new for us, by the way. We made that point in chapter 9. We said that for aldehydes and ketones, these 2 reagents are interchangeable. But as we're about to learn when we get to chapter 10, with carboxylic acids and esters, they are no longer interchangeable. So we'll get to that. That's after our exam too. I think today we're done with exam 4 material. And then we had a couple of oxidation reactions. We said, what is the reagent for Williamson ether synthesis? Usually that's done with an alcohol and an alkyl halide. So yeah, we covered that in chapter 8. And the end result is going to be an ether. So remember that we said that if you treat a simple sugar like this with aqueous bromine, this is an oxidizing agent, but a relatively mild one. And so as a result, you know what? I'm just going to double check that I don't screw this up, because I do not want to lie to you. Let's see. That's what I thought. This will oxidize only the primary alcohol at the top of the molecule to, so I mean, do we need any catalyst? No, I don't think so, not typically for Williamson ether synthesis. But aqueous bromine will give you this oxidized compound such that we've only oxidized the aldehyde functional group to a carboxylic acid. Everything else is untouched. Which again, given my instincts as someone who is a little experienced in organic synthesis, I can't tell you how much I find that absolutely astonishing. That something like aqueous bromine could be so specific. And then the other one we learned, I'm going to go way out over here like this, well, maybe not quite that far. I'll put the structure over here. The other one we learned is warm nitric acid. So nitric acid and heat, that's a stronger oxidizing agent. And that one, in spite of being stronger, is still pretty darn selective. This will oxidize the aldehyde functional group and the primary alcohol at the bottom of the molecule. What is its property that it can oxidize? Well, in both cases, the atoms in the starting material are in a higher oxidation state than they'd like to be. The oxidation number of the bromine in elemental bromine, trick question, it's 0, right? That's what it is for any pure element. And bromine would much rather be in the -1 oxidation state. It likes being the bromide ion. So in order for it to be reduced from 0 to -1, that means it oxidizes something else. That's again that frustrating term, oxidizing agent. Something that's an oxidizing agent doesn't itself oxidize. It gets reduced. It oxidizes something else. So that's one of the hardest things in Gen Chem, along with ions. Anyway, nitric acid, same idea. If you work out the oxidation number of the nitrogen in nitric acid, it's +5. That's the highest possible oxidation number that nitrogen can take. And it would like to be pretty much anything lower than that. So that's why you oxidize both the top and bottom groups. But again, the OH groups on the middle carbons are untouched. So that's another reaction that we learned the other day. And with that, I'm actually out of time. So if I'm not wrong, we start chapter 10 next time on esters and carboxylic acids. And all we have left is that chapter plus the chapter on proteins, and amino acids, and all that side of life. And so, we're going to have a couple lectures on chapter 10, but that material will not be on exam number 4. That'll be in the final exam. So I think with this officially, we're done with exam 4 material. So other than that, have a great day, and I'll see you all on Wednesday.